Okay. Thank you. Welcome, everyone. I guess everyone is sleepy now after lunch, so I hope it will be entertaining enough so you don't fall asleep. My name is Csaba Fitzl, and I will talk about some macOS vulnerabilities hiding in plain sight. A few words about myself. I'm currently working for Offensive Security, and I'm the lead content developer for our macOS control bypasses training. I'm also doing macOS vulnerability research in my free time as a hobby. I used to be a blue teamer for a very long time and also a bit of a red teamer. I'm married, have 2 kids, and I really love to do trail running and hiking. So what I will talk about today, there will be a short intro about the main idea behind this talk, and then I will talk about 3 different vulnerabilities. One of them is a privilege escalation, then we will see a TCC, a privacy bypass, and then a sandbox escape. For each of the vulnerabilities, I plan to give some technical background of the given process that was exploited. Then a few words about the original vulnerability and exploit that was publicly available. And then, of course, the new vulnerability and the exploit I found. So the idea behind this talk is we used to say that we can see the forest for the trees, which usually means that there is something obvious and we don't see it in the background. And that's probably because we are so focused on a single thing that we miss some context or miss some background or just other stuff. I think it's a human thing, so it's natural. And I think nowadays, many times we also rush reading many articles on a daily basis. Like personally, I have a lot of articles that I want to read and sometimes just scroll through or really don't give like a big high attention to them. But actually there are some articles which I tend to go back and read them again and again for some reason, maybe because there was some information in it which was interesting and I don't remember anymore and I need it again, or it was just simply interesting. And I kind of read these vulnerability write-ups online. And there are a few that I read like many times, really like 10, 20, 30, 40, whatever, like really a lot of times. And eventually, in some of these write-ups about specific vulnerabilities, eventually I found a few vulnerabilities that was kind of hidden already in the article. So this is what the talk about. So the first one is a local privilege escalation in preferences. What is preferences, or the CF-prefs-D? The CF-prefs-D stands, I guess it stands for the Core Foundation Preferences Daemon. The Preferences API lives in the Core Foundation framework, so I think the CF-prefs-D is, with the Core Foundation Preferences Daemon, is a good resolution. What it does, it's a system-wide, so there are 2 daemons, one for the user mode application and one for system-wide application that runs as root. And it stores basically preferences for the application. So there is a preferences API on macOS, which we can call from our application and basically store specific preferences, values, what we want through this API. And under the hood, the preferences daemon, it will store all these preferences in various files. We can, as said, we can either interact with it through the preferences API, or we can also interact with it through XPC, which is a macOS-specific IPC inter-process communication mechanism. Basically, on macOS, we interact with most of the daemons through XPC or with Mac messages nowadays. So this is the daemon, and let's see what was the original vulnerability. During the Pwn2Own 2020 contest, there was a 6-step exploit chain to compromise macOS from Safari to the kernel. This is a really nice chain, actually. And one of the steps involved was a privilege escalation step. And in this privilege escalation, they exploited the preferences daemon. What they could do is create an arbitrary, change the ownership of an arbitrary directory on the system. So this was the vulnerable code, what we see on the screen. The way they exploited it, they used symlinks, and basically it was a race condition bug. So they could put symlinks and eventually change the ownership of a custom directory. If you can do that on a macOS, then it's a trivial privilege escalation from that point. What they did is they changed the ownership of the etc pemd directory. This is where macOS and actually many other Nix-based systems stores the PEM configuration files. These are, PEM stands for pluggable authentication modules. So these are modules that we can use to configure the authentication or password stuff and so on. So they changed the ownership of this directory and then changed the sudo config file. And the new configuration was basically whenever they type sudo, it will auto-elevate to root without a password. So it was a nice exploit. So Apple fixed it, and the team reversed the fix, and they published it during the Black Hat talk. And I believe also it's in their write-up. So Apple fixed it properly. So now the preferences daemon no longer follows symlinks, and we can no longer exploit it. But there is still some issue with this code. So the original one was fixed, but there are still two parts in it which are executed without any further checks. One is mkdir@, which is creating a directory, and then fchon, which is changing the ownership of the created directory. So although we cannot change the ownership of any directory on the system, what we can still do is create a new directory with our user as the owner, which can still allow us to escalate privileges. So I found two ways to exploit it, and there might be others. Unfortunately, none of these methods are perfect. But let's see how they work. So what we can do, again, is just create a directory anywhere on the system with our user being as the owner. So macOS and other BSD systems has this thing that's called periodic scripts. These are maintenance scripts run either daily, weekly, or monthly. These scripts will be run as root. These scripts has a configuration file in the etc defaults periodic.conf, and this configuration file defines a location for basically custom user scripts. And this location on macOS is the USR local etc periodic directory. Now, this directory doesn't exist by default. So what we can do, we can create this directory with this exploit, place our script there because we will be the owner of the directory, and whenever the periodic scripts will be executed again by the system, our script will be executed as root. The main issue with this method that it's slow, like it can take up to a day for you to get a root shell. But if you have time, like if you are on a slow red team engagement or you are a nation state, you can wait a day. So it's not a big issue if you are not in a rush. Now, but this method won't work beyond Big Sur 11.5 because I had another vulnerability submitted to Apple, and that was related to Homebrew. So Homebrew, if you don't use macOS, it's basically an open source package management system, and you can install various tools with that pretty easily. And what it does, it will set the USR local directory ownership to your main admin user. So, and basically Homebrew opens up this directory and creates a vulnerability on the system. Because again, you can create the USR local etc periodic directory, then place a script, and you can go from admin to root, which is a secondary boundary on macOS. So what Apple did, now the periodic scripts will check the ownership of the script and will execute the script as the owner of the script. So it's a nice fix, but it killed this technique, essentially. And here's the demo of the exploit. So we can see the USR local directory is empty. We run the exploit. And now if we list it again, we can see that the new directory was created. And even our script is there. And then I kind of simulate the execution of the periodic scripts, because that would be like a real long video to wait for that to happen. And once we execute it, we can see we have a terminal popping up as root. So there is another way to exploit it. On macOS, there is a tool called sysdiagnose, which always runs as root. And if we do a strings on sysdiagnose, we can see that there are a lot of references in this binary to other binaries in the USR local bin directory. Now, these binaries don't exist on macOS because, again, the USR local is by default empty. So we can basically create all these binaries and wait and see which one is executed. Sysdiagnose will not execute all of them, but some. I kind of started to report them to Apple because of the Homebrew issue I described earlier, and they actually fixed many of those, but now I stopped reporting those eventually. There might be still some you can find that it's executed, but I'm not sure at this point. But this method is also not perfect, because you cannot just execute sysdiagnose as is. The way you can execute sysdiagnose is either run it manually as root, which is problematic because your privilege escalation depends on the user doing some actions. You can also open Feedback Assistant, which will execute sysdiagnose as root. The only problem is that when you open Feedback Assistant, it will not start sysdiagnose automatically. You need to do a new case or something like that, and then it will start it. I actually took a look how Feedback Assistant, which runs as the user, can start sysdiagnose as root. And it has some special entitlements, some special rights embedded in its code signatures that allow it to call a daemon, which will call sysdiagnose as root. So you, as the user, cannot replicate its functionality, fortunately or unfortunately, for me as a pen tester or researcher. But as for security, it's actually good that we cannot do that. And the third method to execute sysdiagnose is through a keyboard shortcut, which is Command Option Shift Control period. So it's like a 5-key combination to press, and then sysdiagnose will run. You cannot do this programmatically on macOS, so you cannot just do like keystrokes from an application. So again, it's not a perfect solution, but it's a solution to escalate privileges. So the next vulnerability is a TCC bypass. What is TCC? it's the privacy framework on macOS and also on iOS or all the other Apple software. That's the daemon or process that's responsible for all those pop-ups that you get when this application wants to access your microphone. Do you allow it? This application wants to access your camera, your documents, your whatever. Basically, this framework controls access to resources that Apple consider as private. So this includes, again, microphone, camera, your documents folder, your desktop folder, your contacts, your messages. I think they have like 20 categories for privacy. And this is done by TCC maintaining two databases, one system-wide and one per user. Some of the settings are global settings. For example, rights like full disk access or I think screen capture are like global settings, and microphone and camera are like per user settings. I will not talk more about what is TCC and how it works. If you want to know more about it, I refer to one of our previous talks with Wojciech Regula. We gave a talk on TCC. It's called 20 plus ways to bypass your macOS privacy mechanism. Both Wojciech and me keep exploiting TCC very badly. So it's a good idea, but it's not perfect. And we also wrote quite a few posts about it. Okay, so let's see the vulnerabilities. So the original vulnerability was actually used by a malware, which is very unusual. macOS malware, I think it's not so sophisticated nowadays, but there was a malware that actually used the TCC ODay exploit. So what they did, or how the exploit worked, they enumerated the applications on the system and found, let's say, Zoom. Typically, Zoom has access to your microphone and camera because otherwise it couldn't work or fulfill its functions. And then they took the Zoom bundle, the Zoom application, and they created their own application and put it inside the Zoom bundle. On macOS, applications are so-called bundles. It's basically a directory, very specific directory structure, which is called a bundle. Basically, the entire application is self-contained inside that bundle. So they took the malware created its own application to, let's say, capture microphone, and they took that application and copied it inside Zoom. And whenever they executed the malicious payload, the system was confused, and it thought that it's not the malicious app that it's running, but it's Zoom that is actually running. And because Zoom has microphone and camera access granted already, that malicious component got also microphone and camera access. So they confused the TCC framework with the location of their malicious payload. So macOS wrongly identified the bundle, which can be already a hint for the underlying issue here. So this was fixed by Apple, and then came Mickey Jin from Trend Micro. He does a lot of cool macOS research and does a lot of vulnerabilities nowadays, and basically he found the bypass for Apple's patch. What he found is that if he creates an application, so let's keep Zoom as an example, if he creates a fake Zoom application and gives it the same bundle ID as Zoom, which is in this case us.zoom.xos, the system will be confused again, and so the TCC database doesn't store the location of the application. It only stores the code signature and the bundle ID. of the application. And what it did, it took the bundle ID and checked, okay, where is the application for this bundle ID? And the system came back with 2 locations, but it took the first one that already existed, and in this case Zoom. And TCC verified the code signature of the real Zoom application on the disk and not the fake application. And because the real Zoom application got already the required rights, it was confused again, and it granted the same access for the fake Zoom application. Again, the issue was that the system checked the code signature on the disk for the wrong bundle. So what's the problem here? The TCC database, again, stores the code signature properly for the application, stores the bundle ID, but in both previous cases, the core issue was that it didn't verify the code signature of the actual process running, but it verified the binary on the disk. Now, on macOS, you can delete the binary of the application. You can delete the entire application bundle, and the application will keep running. You cannot do this on Windows. So if on Windows you have a process running, you cannot delete the underlying binary. On macOS, you can freely do this. And this is why it's important to always verify the code signature of the running application. And actually, this is what the system normally does in every other place, except when the application doesn't run yet. So like Gatekeeper will verify the application on the disk, but in that case, it's actually priority execution. Even if we talk about XPC or Mac connection verification, when we want to verify the code signature of the connecting process, we actually have to identify the connecting process through the so-called audit token and verify the code signature associated with the audit token. Even if we use the process ID is insecure on macOS because it can rotate over, or we can reuse it with forks. So we always actually have to use the audit token. Like on this verification for like XPC is not even really an option, or doesn't even come up as an idea, although I saw vendors doing that. And again, if we go to MFI, which is the Apple Mobile File Integrity Process, which is responsible for all the code signature and code integrity verification on macOS, it all works on processes and not on disk images, compared to TCC, which actually worked on disk images. So, how we can exploit it, this issue in a general way. We make a fake application with the same bundle ID of another application that we want to impersonate. Let's say that way. We start our fake application. We copy the real application over our fake application, so we overwrite ourselves. We will keep running. Then we initiate some privacy-related action, like accessing the microphone or camera, and then TCC will come and verify our application binary on the disk, which was overwritten basically by the real one, so it will give a pass, and that's it. We bypass TCC with this simple trick. So we developed this exploit with Wojciech, and we kind of reversed the vulnerability together. So he had another version to this. If we make a fake application, we can embed it inside the donor application, start the application, and kind of, again, copy over the donor application over the embedded application. Here we also need to use the same team ID. Essentially, it's very similar to the previous one. So here is a short demo of this. Again, we keep exploit Zoom. There is nothing wrong with Zoom. It's just a good example, I think, and many people use it. So if we can see that we have the Zoom application. It has camera and microphone permissions, and we also check the configuration. So we can see that Zoom, and only Zoom, has access to the camera and microphone on the system. And then below we have our fake Zoom application, which obviously doesn't have any of these rights. And then we start the application. And then we can see that the size of the application is growing. That's because I copy over the original Zoom application. And once it's copied over, I start recording with the camera. And I made like a 10-second clip of myself with the camera. And we haven't seen any pop-ups or anything like that. So normally, this action would minimum generate a pop-up that, hey, this application wants to access your camera. And also, it would require the COM Apple security device audio input and COM Apple security device camera entitlements as well, to even ask for the permission. So Apple fixed it, and finally they actually verify the code signature of the processes. Now the last vulnerability is a sandbox escape involving the disk arbitration service. What is the disk arbitration service? It's a system-wide daemon defined as one of the launch daemons, so it will run as root. It also has an XPC service offered with the COM Apple disk arbitration DName defined, and it can manage disk mounting and unmounting for us. So it provides a higher level API than the regular mount or unmount syscall, but under the hood it will actually call the mount and unmount system calls. It also allows us to, let's say, hook the mount operation or subscribe to the mount operations, and we can basically allow or deny a mount action from our application through the disk arbitration service, but that only works if the other application uses the disk arbitration API and not like direct mount system calls. So why do we like it as vulnerability researchers? Because it runs as root, it's unsandboxed, its service is reachable from the general sandbox. So here we can see a chunk of the application sandbox profile, and in the bottom we can see that the application sandbox allows accessing the disk arbitration service. And finally, it's also open source. One of the few projects from Apple that is open source, which is pretty nice because it's much easier to find vulnerabilities by reviewing the source code than reversing. So what was the original vulnerability here? Also from Pwn to Own, here from 2017, the Fern Hicks team found the vulnerability in the disk arbitration D service, and it was a privilege escalation. So what was the issue? They provided a location where they want to mount something, a disk image, and then the disk arbitration service verified if the requesting process have permissions to actually mount on that location. Because if you want to mount on a location owned by root, but you are still a user, the disk arbitration service should deny that action, because that's like a trivial privilege escalation from that on. So what it does, it will basically verify the ownership of the target directory with the calling process. So it resolved the path, it verified the location, okay, is it a go or no go? And then if it was a go, it did some further stuff, and then eventually it resolved the pass again, and then did the mounting. So there was a time of use bug here, because it resolved the pass twice. So what the team did, using symbolic links and arrays with symbolic links, they can pass the verification with, let's say, a real directory, then delete that, and then create a symbolic link there and point it over to another directory. And upon the second resolution, it will be resolved, and then the second directory will be mounted over. Basically what they did, they mounted the EFI partition, which is admin writable, over the cron tabs directory, and they created a new root cron job there and elevated to root. So the new CV, actually this is a bit of outlier from the other two, because it wasn't directly in the article, but the new disk arbitration service, the latest one, have two checks now. So there is a fixed check for the user permission thing, and there is also another check for the sandbox information, because again, this disk arbitration service runs as unsandboxed, and if a sandbox process would like to mount in some location on the system, the disk arbitration service has to ensure that the sandbox process has access to that location. Otherwise, it would be a sandbox escape. And there is a new check for that, which is, of course, needed. But it wasn't implemented properly. So if we check the old vulnerable code path, or at least part of it, for the user permission verification, and the new sandbox check in the new code, we can find similarities. So we have the same pass resolution. Then again, we check if the pass is valid. And then the old code, which did the user verification, did the check there, and very similarly, the new code for the sandbox check does the check as well, again on the resolved pass. So again, the code is very, very similar, and turned out to be that the sandbox verification is vulnerable to the same race condition as the user verification was in the past. So I actually wanted to test it first, because I think exploiting race conditions is not trivial and subject to many errors. So I wanted to be sure that indeed there is a race condition. So I created a sandbox profile which didn't allow mounting to the private temp disk folder. And I started a terminal with this sandbox profile, and then made a test mount on the temp disk directory, which wasn't permitted, and then did a test mounting on the temp disk too, which was allowed because that's not restricted by the profile. Then I attached a debugger to the disk arbitration service, which you cannot do normally, so you need to actually enable system process debugging in recovery mode for that to work, but at least you can debug the processes. So I set a breakpoint on the sandbox check function, and then started the mounting again on the temp disk2 directory. Now we hit the breakpoint with the sandbox check, we do a finish, so we run until the end of the function, and we can see that the return value from this function is 0, which means it's permitted. So the actual mount is permitted by the sandbox check. And at this point, what I did, I deleted the temp disk2 directory and created a symbolic link called temp disk2 and pointed it over the temp disk directory, on which location we shouldn't be able to mount anything because of the profile, And then I continue the disk arbitration, the process. And then if we check the mount locations on the system, we can see that we successfully mounted over the private temp disk directory. So indeed, there is a race condition there. Now the question is how we actually exploit this to escape the sandbox. It turned out to be not trivial solution. So the first question is, okay, what we will mount to escape the sandbox? The EFI partition is not in play. For one, now the disk arbitration service specifically checks the GUID of the EFI partition and will simply disallow it. The second part is we wouldn't be able to write there anyway because we are assumed to be inside the sandbox, which doesn't have access to the EFI partition or even if it's mounted then to that location. So that doesn't work. Okay, and then basically the other option is to mount a custom DMG. DMG is like a disk image on macOS. Okay, let's mount a DMG file, but the problem is that disk arbitration D service doesn't work with DMG files. It works with dev devices, like the /dev/ something device that was created. We need to map the DMG file to a dev device, which is problematic because the process which can do this is called the disk management daemon, and that daemon is not reachable from the sandbox. So we cannot call the disk management daemon to map the DMG file to a dev device for us because we are sandboxed. But what we can do on macOS is run the open command, so call open and our DMG file. And what will happen on macOS, it will try to open that file and it will call both the disk management daemon and the disk arbitration daemon. And first, the disk management daemon will map it to a dev device, and then the disk arbitration daemon will mount it to the default location, which is inside the /volume/ the disk name. Which is nice, because we managed to map the DMG file to a dev device, but it got also mounted to a location where we will not have access. So we need to unmount it, which luckily we can do because with disk arbitration, the service also offers unmounting, and there is no sandbox check on the unmounting part. So we can just unmount the mounted disk, and the dev device remains in place. So, okay, the first problem is solved, so we can mount a custom, or we can get a dev device from the DMG image. Now, the second question is, okay, we can mount it, but then where do we want to mount it? There might be many solutions to this. I choose the preferences directory. So the preferences directory sits in the home folder, the home library preferences. And the macOS terminal has its preferences file there as well. And it has a specific preference, which is a command string that will be executed upon launching terminal. So if we create a new terminal preference file with a custom command, like a custom shell command, it will be executed when we launch terminal. And because terminal is unsandboxed, this command will be executed unsandboxed. So let's try to put this all together, how we escape the sandbox. So we drop a DMG file on the system. We can do that from a sandbox. Certain the locations are limited, but the places doesn't matter. Then we will call open on the DMG file. At that point, and we also unmount it. So at that point, we will have a dev device created. And then we will basically start a race with a symbolic link pointing to the preferences directory and alternating the symbolic link with a real directory. And we will start a loop, and we will try to call the disk arbitration service to mount that, to mount the dev device for us on the fake directory, which we alternate with the symbolic link, and eventually we check if there is a mount on the library preferences directory. And once we manage to mount the disk over the preferences directory, we can simply call open terminal. Terminal will open and it will execute our custom command. So this is how it looks like. So this is the terminal preferences, the profiles. We can see that there is the run command above there, which is empty right now. And then we have our application, and it has the sandbox entitlement, which means it will be run as sandboxed. And if we check the mounts, we can see that there is no mount on the preferences directory. And then we start our sandbox application. And it will start the mounting, the race condition. And actually, yeah, just in a few seconds, it managed to mount over preferences. So we can now see that there is a mount over preferences. We can also see that there was a command run very initially. And yeah, we can see that there is our command. So that's it. So we managed to escape the sandbox. So conclusion, I think turns out that sometimes it's worth to read write-ups really carefully or going back to them multiple times and read them again. And I think it's also good to revisit old documentation, even if it's our own, or old write-ups, because we can spot new things in it. Again, these vulnerabilities didn't occur to me in the first time. I read them many times, and eventually it kind of clicked in that, hey, something is not right here. So there is something wrong with the code or with what's happening here on the system. And sometimes it's worth to slow down. Thank you very much.
Thank you. Are there questions? Maybe I ask one which may lead to some discussion on different operating systems. So often some people say macOS is like more secure than other operating systems. From your opinion, would this be true, or is it like similar to other operating systems? It's the same bugs?
In my personal opinion, I think nowadays every operating system security is, I would say they are very similar. So I think Windows, Linux, macOS, they are pretty good nowadays. All of them has pretty decent security, but there is always a way around. So I think it doesn't matter which one you take. There will be always vulnerabilities. There will be always ODays. Like if we checked the monthly, or with Apple, the bi-monthly security updates, we can see that there are always RCs, there are always lots of vulnerabilities on all of the operating systems. So I think they are they work differently, they approach security differently. So macOS is very different from Linux or Windows, and vice versa. So they approach security differently, but all of them are, I would say, very decent nowadays, although we can always exploit any of them.
Okay, it seems like the political correct answer. Are there further questions? If not, we thank the speaker again.
Thank you.